this is going to change as time goes on. I feel that heat blast, and I hope it's not too bad for you guys. It's somewhat historical to explain why this thing is called a one-prop Z-int. Thank you, Brandon. You're a wonderful cameraman. I appreciate that. So what I want to do is I want to throw back an old image you saw in 243. These are binomial distributions. What I'm letting happen is I'm letting the end, the sample size, get larger in each of them. And we saw this back in the day, and we knew that eventually, over time, if you let n get big enough, the bell curve just shows. It appears. I mean, it's a function of the function, so to speak. Somebody asked me earlier, Tim, I think it was you, about algebra. You know, when you graph anything in algebra, is it based on an equation? Absolutely. Just like the binomial is based on an equation. The values near the average are higher than the values in the extremes. So Michael, here's your 68%, here's your 95%, and so forth and so on. Beautiful. But what's the big assumption about all those bell curves I just showed you? Every single one of them has, I mean, the sample sizes are increasing, but every single one of them is alike in that what is true on that. Where's the center? The same place, halfway across. 50% is your average. So, since 50% is your average, if the sample size is 100, 50 is going to be the highest bar. If 50 is your average, 25. If 10 is your average, 5, and so forth and so on. If 3, then 1.5. So your highest point of the bar is always halfway across. And this is great if you know that your sample size, or if you know that your percentage is 50%. Gesundheit. Do you think that the foreclosure percentage is close to 50% from our last experiment? It's not. It looks like it's close to 9%, which is nowhere near 50%. So how the hell can we so brazenly use a bell curve when that's not true? Well, let's explore that. Let's explore what happens if we change P. If we change P a little bit, so we start letting it vary away from 50%. Let's take it away. I intentionally used that one in 243 because I wanted to show you the fusion of one to the other. But what happens if you vary too widely? Well, here's 50%. Now all of these have a sample size of 20. And we'll come back to why. Is that one of you guys?
No.
Hopefully not. What's happening look what's happening to P. P is beginning to creep towards our foreclosure rate. Ah! Our beautiful bell curve is gone. It's been replaced. Ooh, it changed too fast. Hang on. It's been replaced by this goofy skewed thing. Nothing wrong with it. Nothing wrong with skewed distributions. I love them. I mean, they happen all the time. But today in Kate. No, go.
Oh, I said it would be a fun roller coaster.
It would be. Super fun. Actually, death-defying. Probably died. How many of you guys took calculus here with Charlie? Did you guys do the roller coaster? I've seen some like, they would never pass muster in any amusement park roller coasters. Like, oh, then it goes straight down, and then it cuts into 3 circles, and I'm like, you're going to kill everybody on board. Go for it. But if you make it, my God, there's no way you know. So, look, bell is gone. The bell is now gone. It's now a skewed distribution, which means we can't use the Z 1, 2, 3, -1, negative, gone. Unless, and here, we're finally going to answer your question after the break with this. Here we go. Look what happens now. I'm going to use that same skewed 10%. So I'm going to start with that same skewed distribution that we just ended with. So that crazy right-skewed, left-leaning roller coaster. But what I'm going to do is I'm going to start increasing my sample size in that same distribution. Okay, so it was 20. Here's 20. Here's 40. Here's 60. Huh? What's starting to happen as my sample size gets larger? We're starting to get back. I want to back up to that last image. We're starting to get back to a bell shape. Now some of you will notice it's not perfect, is it? It's not perfect. It's not perfectly symmetric. No, it's not. It's a little, notice, right there, right there. It's not perfect. It'll get more perfect the larger your sample is, for sure. Right now the sample is what, 100? It's at 100. So Renee, you asked me a great question earlier about what's the minimum? Hold that thought. After break it, we'll get into it more formally. You might also notice that with a sample size of 100, this horizontal axis should go all the way to 100, shouldn't it? I mean, technically speaking, even if the percentage of success is 10%, you should be able to explore the possibility of getting 100 successes out of 100 with a 10% success rate. It shouldn't happen very often. That's the whole point of 10% success. It means it should have happened 10% of the time, which means it should have happened 10 times. Notice where the largest bar is. So the lion's share of what happens right there, and that part's the bell. So statistically, and using calculus, you can just essentially ignore that tail over there because it sums up to less than 1% of 1% of 1% of the curve. And as n gets larger and larger and larger, that tail that's over there means less and less and less. And we're finally getting, but you guys are definitely getting that. Okay, I need to walk around a little bit because the room's getting hot. Look. What's the minimum sample size? I want to come back. Let's take 5, yes? If you want to add those quizzes to the pile now, by all means, yes, let's do it. Yes, good stuff. Go!